This is Geometry Chapter 4, Section 8, in which we will be studying triangles and the idea of coordinate proof. And you've already met several different forms of proofs. You've met the paragraph, the two-column, and the flow proof. Now we have one more that we're going to add in, called the coordinate proof. And the idea behind a coordinate proof is that you use figures drawn in a coordinate plane, so in an xy axis, and then you use algebra to prove things. So it's not the same kind of proof at all. And I think you might, once you get the gist of it, I think you might like these proofs better than the other ones. When we place our figures, in this case we're primarily going to be dealing with triangles again. When we place these things in the coordinate plane, there are some basic rules we need to follow. If we can do it, we want to use the origin, either as a vertex or as a center line, center point. We do that because then we make our arithmetic simpler because we're using 0, 0 as one of our points to work from. Okay. When we can do it, we want to place at least one side of a triangle on an axis, either the x-axis or the y-axis. Again, that's to be able to use 0 as part of our calculations. We could draw the triangle way off somewhere up, at like 4, 6 or something, but then our arithmetic has to involve 4 and 6, as opposed to working around a number 0. That's a lot easier to work with in the arithmetic. If we have an option, we want to keep the triangle in the first quadrant. Now, sometimes, and you'll see this in a little bit here, it's not always the best choice to keep it in the first quadrant, but as much as you can, you want to stay in the first quadrant so that all of your numbers are positive, as opposed to having positives and negatives and having to remember how to subtract with those and things of that sort. If everything is positive, it makes things easier. And as much as we can, we're going to use coordinates that make the computation simple. Okay? We're going to try our best to keep things as simple as possible, to keep the arithmetic easier, keep the algebra easier. Now, I know that stuff so far is cryptic because you haven't seen how it works, but I want you to have the rules so that we can work with them. Now, here, they're asking us to position and label an isosceles triangle, JKL, on the coordinate plane so that we have a base, JL, which is A units long. We have a vertex, K, which is on the y-axis. And the height of the triangle is B units. Notice we've got an A here and a B here. We don't have actual numbers, we have variables to work from. Okay. Now they tell me specific things about this triangle. First, they tell me the name of the letters, J, K, and L. They tell me JL needs to be the base of the isosceles triangle. That tells me that the other two are the congruent sides. Vertex K needs to be sitting on the y-axis somewhere. Well, you'll notice I put K on the y-axis. Now, I could have put it anywhere I wanted to, as long as it was on the y-axis. I just picked a spot and put it there. And the height of the triangle is B units. Well, the height of the triangle would be from 0, since I put it on the x-axis, from 0 up to K. That would be the height. Well, if this distance is B units, then the coordinates of this point would be 0, B, whatever B happens to be. If they tell me they want a distance of 3, then I would have 0, 3 would be the height, or the coordinates for the height point. Now we still have to deal with this other side down here, JL. And they said they want that side to be A units long. So from J over to L, the distance is A. Well, that's not too hard to figure out. If the distance is going to be A, then each side of this would have to be half of an A away from the center point. So that would be negative a half an A, 0 for this point, and positive a half A, 0 for that point, so that the total distance is A. From J to the center line, to the y-axis here, is half of an A, and this is also half of an A. Makes a whole A. Okay. This is the idea of what we're going to be working with, is putting these things in so that we have convenient things to work with. You'll notice here I used as many zeros as I could get away with, so that as I go along, I don't have to work as hard. Okay. Here's another problem. They want us to name the coordinates of this isosceles triangle XYZ. Okay. Well, I guarantee you can tell me the coordinates of point X, because point X is at the origin. So X has to be 0, 0. Now let's consider Z. Z is on the x-axis. So what would the coordinates of Z be? The coordinates of Z would involve some value A that they gave us, and then its y-coordinate is 0 because it's on the axis. Okay. Now we get to the fun one, y. We know from our earlier studies of isosceles triangles that the altitude here, the vertical line, cuts the triangle in half. So the x-coordinate would be half of whatever A is. So the x-coordinate here would be a half an A. We don't know anything to tell us about the y-coordinate, so I'm just going to call it B. Okay, there's nothing that indicates what it should be. You know, could it be the same as A? Sure, it's possible. Could it be a half an A? Yeah, it could be. We don't know. We don't have any idea what else to call it, so we're just going to call it a different value from the original. Since they gave me A, I'm just going to pick B. If Q is your favorite letter, you can pick Q, and that's good too. Okay. So we're going to ask you to pause your video here as usual and take a chance at naming the coordinates for this triangle. It's an isosceles right triangle. So pause here, work the problem, and then check your answer. Okay. Again, I'm sure you picked up that B is the origin, so the coordinates for B are 0, 0. The coordinates for C are easy enough to pick up because it's on the x-axis, so it would be A, 0. Now here's the part that some of you may have missed. Since they told me this is isosceles, if this line is A units long, then this one is as well. And since it's on the y-axis, that would be 0A. Okay. If you put 0B, then you miss the part about it being isosceles, and that was the key piece there. Okay. Last thing we're going to throw at you here is to actually write a coordinate proof to show that a line segment joining the midpoints of two sides of a triangle is parallel to the third side. So I have a triangle here, and I've connected the midpoints of two sides, so there they are, and I'm trying to show that this side, this line MN, is parallel to AC. And we're going to do this with coordinates. So we need some coordinates. A is an easy one to get the coordinates of. A is 0, 0. C, we can get the coordinates of. We don't know how far this is over, so we're just going to pick something. And for the sake of simplicity, I'm going to pick 2A. All right. Now, the reason I picked 2A is I remember reading that we're going to talk about the midpoints. We're going to be taking half of things. So I'm making it where my fractions aren't going to be a problem. Now, B, we have no way of knowing what either coordinate should be. So I'm going to call it 2B and 2C. Again, thinking ahead that I'm going to be dealing with midpoints, so I'm going to be dividing by 2. So I made everything have a factor of 2 so it'll reduce out easier. Now our job here is to show these two lines are parallel. That means we need to show that they have the same slopes. Well, to find the slopes, we need to know the point for M and for N. And that's going to call for the midpoint formula. 0 plus 2b over 2 and 0 plus 2c over 2. Well, that's 2b over 2, which is b, and 2c over 2, which is c. We'll do the same thing for point N, find its midpoint, 2b plus 2a, and 2c plus 0, both over 2. So we get b plus a for that value, and c for this one. Now we're ready to find some slopes. The slope of line MN is C minus C over B plus A minus B. Well, C minus C is 0. B plus A minus B is A. So we get a slope of 0. Slope of line AC, 0 minus 0 over 2a minus 0. 0 minus 0 is 0, 2a minus 0 is 2a, and so we get 0 again. Since the slopes are the same, then we know we have parallel lines. Okay? It's a little bit different way of thinking about things, but notice something that we didn't have to do in this proof at all. Nowhere did I give reasons. I didn't have to say given, I didn't have to say definition of, I didn't have to say theorem, anything. The closest thing to a reason I had to give was this last thing that tells me how I know the lines are parallel. That's why I think after you get the hang of it, you'll like these proofs better than the other ones. Okay. And as always, if you had questions along the way, hopefully you wrote those down. Bring them in with you, and we will see you in class.